All right, so we open up a new script here, and again we save it. Let's save it as beam. All right, so always keep in mind that when you're saving, do not create any spaces between your file name, and also do not start off with a number. Right? So we could this could be, all right, so this is beam example 4.1. All right, so we start off the same way we started off before. CLC, clear all. Right, and then we have these symbols or the symbolic notation. So symbolic notation would be as we said, we have the parameters of the beam symbolic, and also we have the elements that we want to find, which is the displacements and the forces. So we can start off with L, right? E, I. Right, we could also have now phi 1. If we just go back through it and realize what we need to find. Right, our load was P. Our length is L, where we have that already. We have R2, R3, and the reaction moment at 3. Right, so I'll just quickly go back through. Let's go through this. Right, so this is our beam. Right, let's quickly go over here. Here we have the 1y, phi 2. Right, those are unknown because that will be free to move. Here you would have d2y equal to 0, and you will have a phi 2, right? Because it will be allowed to rotate. And here you will have d3y and phi 3 equal to 0. Right, in terms of the forces side, here the forces P and M1. Well, M1 is equal to 0 because it's a free end. Here you will have R2, and you will have M2. Right, but M2 now, yeah, it will have one M2, right? And then here now R3, and then you will have one M3. Right, so our force vector would be P0, R2, because the beam is supported and it's allowed to rotate, then M2 will be 0, so I should keep this at 0 here. And you have R3, M3. Right, so these are our force vector. Our D vector would be At d2y is 0. Did I make my do I tell my the wrong thing there, man? Just phi 1, not phi 2. Right, that's our d2 or d vector. Right, so our unknowns are R2, R3, and M3, D1, phi 1. So again, we have 6 unknowns. Right, so we would have 6 equations and 6 unknowns. Right, 1, 2, 3, 4, 5, 6, 6 equations. And 1, 2, 3, 4, 5, 6, 6 unknowns. Right, P is given, but we're giving it as a symbol P, right? But P could be a value. Right, so going back to the MATLAB now. Right, so going back to the MATLAB. Right, we have our symbols, the LEI, phi 1 dy, d1y, phi 2 d2y, phi 3 d3y. And then our unknowns here, P, R2, R3, M3 or reaction moment M3. Right, so you can make a comment here and you could say our M3 is the reaction moment M3. If I just want to be clear. Right, so we could enter now the stiffness matrix because that was the next step. Right, so you go back to here, and this was the spring element. So you can enter the global stiffness matrix, then the D, then the F, and then the procedure will be the same. Right now, the global stiffness matrix, we have to decide how we want to do it. If we want to enter the entire thing one time, or if we want to build it. Right, so we could build the entire thing, and we could say, okay, K is equal to, so we would need now to pull up the stiffness matrix. Right, so you could follow along in your notes there. I'm not sure if I could split the screen here. All right, so by chance you all seen the screen split, or you just seen one screen still?
You see in this split.
Right, good. So we see any K matrix that we're going to enter. Right, so it'll be 12, 6 times L. Right, so when your card is write 6L, you have to put the multiplication. Right, so that's the first row complete. Right, so if you see I make any mistake, just point it out to me. right? So if something getting too long to enter, you could continue entering it. You could put a million objects shit on the other, but if it is you want to keep it on the page, you could keep seeing it. Like in our case here, I want to be able to keep the split screen. You could put 3 dots, hit enter, and it will just, what it will do, it will kind of continue the line underneath here. Right? This faint vertical line you're seeing here, this is like a page margin. So if you want to print the code, then this will end up having to print on our next page and it will look stupid. Right? So ideally, if you're doing something to be printed or put in an appendix or something, well then you kind of keep everything within the line. Right? But for the sake of this writing code, there's no need to kind of keep it in that line. Right? But I put in the 3 dots so we could see it here as we're going along. Right? So the next line was 6. All right, so to see if this is looking correct, we just click run here. So long it taken to put together that. Right, so this is the matrix here. Could just cross check to make sure. All right, so looking good, right? All right, so the K matrix looking correct there. All right, so we could continue now. All right, so the next step now, let's go and referring back to the first one we did, the K matrix, and we define the D matrix. All right, so we could go and work on the D matrix now. All right, so the D matrix. All right, so if that is what we were done a while ago. That's D1Y, phi 1, 0, phi 2, 0, 0. And next was the F matrix. That's in matrix X vector as P. Right, so we could run this to see how things looking. Right, so the D matrix. Right, so the F and the D matrix. Right, so the next step we did was, so after we did that, then we did this piece of logic here. Right, where we said, okay, we work out what K by D is, and then we said F multiplied by KD is F, sorry, the F vector minus KD is equal to 0. Right, so we could copy and paste that, or we could just put it in ourselves. Right, so we could say the equations that we want to solve is that is right. So this is the equation, right? KD is equal to F, so KD minus F equal to 0. And then we say the solution is solve the equations, and then what we want to solve for. Right? What we wanted to solve for was the unknowns we had defined, which is D1y, phi1, phi2, R2, R3, and reaction moment 3. Right? And make sure you always close all your brackets. Because when you close a bracket, you can actually see what bracket you're closing. Right? So when you close this, you see close the square. When you so you can click run now. All right, so done. You see solution pop up here. Right, so again, this is our solution. Right, and the solution now would be in terms of P. Right, our moment. Of course, it will be in terms of P and L. Right, so what we could do, we could actually do a split screen here, and we could actually probably try and go through the solution. Right, so this is their solution. So D1y was 7 minus 7 PL cube on 12 here, right? So D1y 7p. So the L is missing. And the EI is missing. So I know that means that the L and the EI, cube and EI is missing. Right, so if we go back to the code now, so this is how we troubleshoot. We forgot to put in the EI on L cube over here. Right, so we need to put that in, so bracket E times I divided by L to the power 3. Right, so we could run this again. Right, so you could see it changes. So 7 PL cube over 12 VI. Right, that's what I get here. Now I notice that this is negative and this is positive, right? So they change that. Well, it's just a matter of the sign. When we are define F as P, remember P acting down on the beam. So if it acting down, we could put a negative sign. So you want to again and we'll see. Right, so now we get negative P here. All right, the other one is phi 1 GPL squared over 4EI. Phi 2. Right, so most of the time if one correct, all will be correct. Because everything is intertwined or coupled with each other. R2. Right, so 512P, which was the F2 in the for the thing. R3 minus 312P on M3. A half PL. Right, so we could come here after if you want. We want to express it. We could, just like how we pull this out here. We could come on, we could do a similar thing here. Just to get the equations coming out. So you could put D1Y Right, so you could copy and paste stuff to it. If you, I'd say display all the answers. Right, so that's it in terms of variable form. If you want now, let's just say well, we have those solution, we want to substitute some values. So let's just say we say P is equal to 1000, L is equal to, let's say 0.5, E is 200 gigapascals. I is very small, I is normally small, so let's just say is 2 E by minus say power 6. Right, so that's P. Right, then we could come and say evaluate, let's just say D1Y. Okay, so you can say D1Y numeric is equal to evaluate that. So what I will do now, I will substitute these values into the equation for D1Y. Right, so this is D1Y. This is minus 1.8 by 10 to the minus 4 meters. So minus meaning that it's going down. Right, so that's the nice thing about doing maths like this is that the signs takes care of everything. So you don't have to think about too much. Well, negative, it in this direction, it in that direction. Even your bending moments and your shear force, right? This, for example, is our bending moment because that's a moment at the end. Yeah, R3, R2, all these things are shear forces. Same shear forces you would have learned in strengths and we would have done last year. I'd say substitute P into this and you'll get your shear force at this point. And so the more elements you have, the more points at which you could get shear forces and bending moments along the beam. And that's the basis for how these sites like Beam, Guru, and ThingWorks. Right, so we could say eval, let's just say R2, for example. Right, so because numeric values for P, E, and I and L stored now in the workspace, when we do this now, it will substitute those values into this R2 equation. Right, so the answer is 2500. So R2 is 2500, and that will be pointing in the up direction, which makes sense because we say in the beam, the reaction force will be up like this, right? Up. Right, so that's it really in a nutshell. There another method. What is it? Another method for putting together the K matrix is actually do it from a two element matrices. Right, that's one way of doing it, and again is the same tedious process. Right, what I'll do here is kind of cut to here, and I'll say, okay, let's clear the screen. Actually, K matrix is that. Right, so suppose we want just the first column alone. Sorry, the first row alone. We could say K, we want the first row, and we want all the columns from this end here to this end. So we're going from column 1, we put the colon to column, let us drag this here, to column 6. And what I will do, that will give us just that row alone. Right, so if you want to pull out, let's say pull out or build a matrix by pulling out individual lines, you could do it that way also. Right, so what I'll do here is I'll kind of show how it's done here, right? Save this. All right, so I'll just copy and paste. All right, this is here the matrix for K1. And this is the matrix for the another element K2. So what I've done here, this was a separate method for assembling the K matrix before we just type in the whole global K matrix. But if you want to build the K matrix, then this is one way we could build it. Right, so it's up on the screen here. It will be in a recording, so you can actually pause the recording and see this is another way of doing it. What I did here, I actually pull out row by row and actually assemble the matrix. That is what was done here. Right, so I pull out the first row and then add 2 zeros next to it. Pull out the second row, add 2 zeros next to it. Pull out the third row, add 2 zeros next to it. That's how I did it. Right, let's add this part here. Actually, I'll just share everything here and right, so I'll share everything here so you can actually see how I did it. How I assemble the matrix. Right, but again, this is a tedious process. And I don't expect anyone to do this for when you have 10 elements. Right, so the software, well, Final Element software has methods of assembling these matrices based on the arrangement of the elements. So you won't have to manually do it. But because beam elements are mostly arranged one after the next, it is simple to create an algorithm just to join the matrices together.